Hello everyone, welcome to our talk. My name is Jianrong from 360 Alpha Lab. Today, my colleague Licriso and I are going to talk about our research on bug hunting in Chrome. First, let me give a brief introduction to our team. 360 Alpha Lab mainly focuses on mobile security, including trust zone, kernel, applications like browser, and so on. We have reported more than 300 bugs to top vendors, including 3 exploited chains of Android devices, and won the highest reward of Google VRP program. Our team also successfully pwned many targets in Pantuan and Tianfu Cup contests. So bug hunting is the main content of our work. As a security researcher, it is always a good idea to learn from the old bugs and try to find more. Considering the complexity of the code base, there is a high probability that bugs shared with similar code patterns may exist in many places throughout the code base. Find similar vulnerabilities based on a known one. This is called variant analysis. It can be performed by either manual code audit, automated analysis tools, or just writing your own further seeded with the poke. But to find new bugs effectively, we need to understand the root cause of the original bug, sum up a bug pattern from it, and make sure this pattern is good enough for describing other similar bugs. However, this is sometimes not an easy task because not all bugs can be abstracted briefly, and the way how you mutate the pattern may affect the results greatly. For example, suppose we find an out-of-bounds bug caused by just memory copy. We can perform some data flow analysis on these parameters to other memory copy calls, or we can consider other function calls like memmove, memset, and search the whole code base. Depending on the choices, our results are definitely different. In this talk, we take Chrome as an example to present how to discover new bugs based on historical vulnerabilities. Chrome uses a multi-process architecture which isolates different processes from each other with Sandbox. We are focusing on the code runs in browser process, which means is unsandboxed, and we are going to use CodeQL to help us locate potential bugs quickly. CodeQL is a grid analysis tool which compiles code to a snapshot database and can run queries against it for program analysis. At last, we will share the exploitation strategy of one of the bugs we found to escape the Chrome sandbox. Let's start with a common bug pattern in the Chrome: random from host lifetime issues. So, what is a random from host? It is an object lives in the browser process which represents a frame in the render process. It provides a communication conduct with the frame in the render process. Usually, we can delete a random from host object by just closing the underlying iframe. Many services in Chrome need to access random from host. There are 2 common ways to do it. One is to storing a global ID and using from ID functions to retrieve it back when you need to use it. And the other way is holding a raw pointer to random from host as a class member variable. This means that the developer should take responsibility to observe the lifetime of random from host and clean up the raw pointer when the random from host is going away. So if a service can outlive the random from host and still tries to access the random host object after its destruction, it causes a use of a free bug and can be exploited to escape the Chrome sandbox. A representative example of this pattern is the issue submitted by Theory, which version used after free in installed application provider implements. This class implements a module interface named installed app provider, which provides installed app information related to the origin of the requesting page. we can see that it holds a raw pointer to the random from host objects. This instance is created by a static function named create, and its lifetime is bound to the lifetime of the module receiver through make self-owned receiver function. So the implementation will not be deleted as long as the receiver stays connected. Quite a lot of Chrome module concepts here, but this code can be described in a simpler way. There is no relationship between the lifetime of random frame host and the installed app provider implementation. If we delete the RFH and invoke any method which could access it, the use of the free will occur. In this case, function filter installed apps will do the trick. There are many other known similar issues. So we are wondering whether there are still such kind of bugs exist in Chrome codebase. This bug pattern can be described in one sentence. Any class storing random from host as a room pointer in a member variable could be vulnerable. Thus, a simple grep command throughout the codebase can get the corresponding results. However, this description is too broad to reduce false positives to an acceptable range, so we need to add more specific constraints. According to the bug fixing, a class can get notified of various page events from web contents by inheriting web contents observer class, including when a random from host is going to be deleted. This gives a chance to clean up the pointer to random from host and prevent use of free from happening. The fixing also indicates a way to improve the description. We can filter out the class which is a subclass to web contents observer and implements the random frame deleted method. Similarly, a subclass of frame service space can also be excluded, because the class inheriting frame service space will be destroyed when the random from host is deleted. So, taken together, we can write a CodeQL query, for instance, that meets the following conditions. First, it stores random from host as a room pointer in a member variable. And second, it's not a subclass of frame service space. Thirdly, it's not a subclass of web contents observer, or the random frame deleted method is not implemented. It's not hard to write a CodeQL query to search this. Here is the key part of the query. First, it finds a field which is a room pointer to random from host. Then it says the class is not a subclass of frame service space and not a subclass of web contents observer, or the random frame deleted method is not implemented. Executing this query against a custom-built Chrome snapshot gives us 29 results. We found one true positive after digging deeper through the results. This is very similar to the case I introduced before, and we submitted the vulnerability in this issue, but unfortunately got duplicated, which was reported 1 month earlier. As we can see, random from host lifetime issue is a very common pattern that keeps happening in the Chrome codebase. And because its cause is not complicated, this type of vulnerability will not exist for too long. Now I'm going to hand it over to Liquorsoul, and he will introduce a more complex bug pattern in Chrome.
Well, thank you, Ron. I will show the next pattern, the error return issues. Random frame host lifetime issue is a very common pattern, but because its cause is not complicated, this type of vulnerability will not exist for too long. And searching only based on utility vulnerability patterns without any mutation may not be effective. The way how to mutate the pattern is important. Next, I will describe how we started from a basic vulnerability pattern to do mutate, and finally found 14 vulnerabilities and got 5 CVEs. I take 2 vulnerabilities discovered by other people as example. And first, let's look at CVE 2020 case 461. In the course, there is a possible path that transport complete will call cancel building blob, which has the side effect of deleting this. And the next branch, if blob this is bad IPC, could also be reached. However, since this is deleted, the member variable by the message callback is also freed, and thus the UIF triggered. And the next case, the network process will send readable data to channel through WebSocket channel send frame. But in send frame, file channel could be called if some checks false. In that case, the WebSocket instance will be deleted by doing erase from a STD set which owns it. Same as the progress bar, after returning from the send frame call, the subsequent code continues to be executed, and then UF will be triggered when accessing the member variable readable. From these cases, it can be seen that the root cause of this bug pattern is during the code execution of a class instance, calling other function which could cause the destruction of this instance. When returning to the context of the destruct instance to continue execution, the use of free will occur if any member variable or member function is accessed. We can write a query of this pattern with CodeKL, and the key part of the query is as follows. The managed map type class and the range function are imported from QL libraries published by MMO. The managed map type class is used to define management types such as a set or a map. And the reach function determines the reachability of functions, including the callback functions. After screen, we found several problems on this pattern. Take CVE 2021-1115 as an example. Password protect request is used to check whether a familiar login from or a password reuse event is safe or not. The member function on whitelist checkdown will call fail request proto when several if condition matches. And in method fail request proto, a sample pin request will be sent through send request. But if the serialized information is too large, serialized to string will fall, so the request will be finished immediately. This will erase the request instance from ST set named pending requests. And then the use of free will be triggered when the finish in on whitelist checkdown is called. So our query seems to be effective, but how to mutate the pattern to make them more efficient? Based on the analysis of results, we notice that releasing objects is some unexpected conditional branches is point to be vulnerable. And besides deleting the whole instance during execution, we try to focus on lifetime management of the object referenced by a smart pointer. So we propose such variant. Considering a smart pointer as the Unicode pointer X, its raw pointer to the managed object is returned in a context for subsequent uses, and the X itself will be moved as a parameter to a function. In the function func, if the check condition is not met, it returns early before the ownership of X is transferred to the new owner. This will cause the smart pointer X to no longer be held by any owner, resulting in an unexpected implicit release. The use of free will be triggered when the reserved raw pointer is used later. A new query is required to search for this kind of pattern, so key parts are as follows. Here we use dominies to determine the relationship between the return node and the move node in the control flow graph to ensure that the pointer has not been moved to a new owner at the time of return. We also found several problems with this pattern. Here we take a bug as an example. The ownership of older web content will be passed to source page handle. then source page handle will be moved to maybe start distillation as a parameter. At this time, if the check falls, it will return immediately. Source page handle will be destroyed at this time. All the web content becomes a downlink row pointer, and the use of free will be triggered when accessing it. There are many search results for this pattern, but the return conditions or most results is hard to be met. We want to mutate the pattern more specifically. When editing the query results or error return, we found a strange piece of code. This is a piece of code exists in the drag and drop UI component. Continue drag is a member function of type drag context implement. It calls drag, which is used to execute the user's drag behavior. According to the error return pattern, if we can destroy type drag context implement during drag, a UF will be triggered when accessing the member variable drag controller. When we look for opportunity to destroy type drag context implement in function drag, we found that drag will eventually call run more loop, which will run a nested message loop as follows. So what is the nested message loop? Run loop run will run a new message loop to process system and application task assigned to a delegate associated with the current thread. This blocks subsequent code execution until the exit condition is met. The quit closure is responsible to close the loop when the exit condition is triggered and restore the outer context. Therefore, if we could destroy some instances in the new message loop after we exit the new loop and back to the blocking context, a UF will be triggered when the destroyed instance gets accessed. Take the code of drag and drop as an example. Type drag context implement could be destroyed during the message loop. After the loop access in continue drag, the code after drag will continue to be executed. The UF will be triggered when accessing its member variable drag controller. So we got CVE 2020-16004. Finally, we found 8 UF bugs about the Linux X11 clipboard where the code did not check correctly when using the nested message loop, as well as 2 UF issues related to the message box, and a series of issues in the Ozone clipboard, which are the same as the X11 clipboard. And Google changed the clipboard APIs to be asynchronous instead of using the nested message loops. Take one of the X11 clipboard bugs as an example. When Chrome Password Manager client listens to the past event, it will call read text, and read text will run a nested message loop. If Chrome Password Manager client are destroyed, the UF will be triggered when accessing its member variable words on past code after the nested message loop exit. Well, that's the story of error return issue. Now I will handle the presentation over to Ron. Thanks.
Thank you, Licraso. According to these bugs, an unusual bug pattern like run loop can often open up a new attack surface with more vulnerabilities. Next, I'd like to share how we discovered another unusual pattern, weak PTR optimization, and show how to exploit one of the results to escape the Chrome sandbox. Weak pointers are useful when an object needs to be accessed only if it exists, and the managed object may be deleted at any time by someone else. Chrome implements its own version of weak pointers, named weakptr, and it is widely used in the codebase. The weakptr class holds a weak reference to an object that has no effect on its lifetime. A null test of this class is necessary before any use to ensure the underlying object is still alive. Here is a simple example. Validate the pointer first before calling a method in it. So what if we do not follow the rule and invoke the method directly without any null test after the object was deleted? The implementation of weakPTR may answer this question. weakPTR class overloads the class member access operator to act like a normal pointer for convenience. If the underlying object is not valid, it will return non-pointer instead of the raw pointer. Therefore, invoking the method on an invalid weakPTR object would only result in non-pointer dereference, which is regarded as non-exploitable. However, this is not the truth when we ran a test on kernel build with ASM. We found a code error in which weakPTR being used commented out the null test code, recompiled the kernel, and triggered the corresponding code. Instead of a non-pointer dereference crash, we got a use after free at a valid address. To make things simpler, these example codes can show what happens. The class foo gets an inner pointer to bar, and the get method would return the wrong pointer if isValid is true. But in the main function, the isValid was set to false, so the get method should return null, and the virtual function call on null pointer should crash the process. This is what happened if we compile the code without any compile optimization. However, if we add an additional -03 command, the crash disappeared. The reason why weakPTR did not work as expected is that the LLVM compiler optimized out the branch which get method would return null pointer as a result. More specifically, the compiler recognized that there was a null pointer dereference which belonged to undefined behaviors and chose to remove related code. Unfortunately, this optimization strategy could convert a non-point dereference trash to an exploitable use after free bug. Considering that weakPTR is widely used, the situation accessing the underlying object without null test is likely to exist in many places. In a function body, a weakPTR could be a class member variable, a function parameter, or a stack allocate variable, and the underlying object could be accessed through pointer dereference operator or member access operator. It is not a good idea to take all of these points into one query, so we can search the pattern that occurs in most situations. Supposing the weakPTR is a class member variable and it is accessed through the member access operator. So about the code QR part, we first find the function calls invoked on a weakPTR object. We match the type name and find all access. And the next step, we want to ensure that there's no null test before accessing weakPTR. So the code says that there not exist any if statement which is related to weakPTR. The query gives about 363 results in our testing, but many of them are duplications of the same class. We got 3 CVE numbers after a quick analysis and successfully exploited one of them to escape Chrome Sandbox in Tianfu Cup last year. And again, I'm going to hand it over to Ligraso for the exploitation part.
Okay, thanks Ron. I will show the last section about how to exploit one of the weak pointer bug to escape the Chrome Sandbox in the Tianfu Cup 2020. First, it's about some payroll knowledges. Unlike module IPC, which security researchers have been paying attention to in recent years, the vulnerability we discovered exists in legacy IPC. In legacy IPC, each render process has a single IPC channel implementation go between itself and the browser process. And this is used to send legacy IPC messages between the processes. There are two fundamental types of legacy IPC messages. control messages defined via IPC message control macro, and rotate messages defined via IPC message rotate macros. We now focus on the control messages. As figure showed, control messages generally go between the runtime and the broadside implementation host. All these classes implement IPC sender and thus have a sender method for sending a control message to their remote counterpart. And they implement IPC listener to receive incoming control messages via on message received. The bug we used is a vulnerability in browser-side implementation, so we can trigger it by sending some runtime legacy IPC request. And another prior knowledge is about PP API. We need a sender to send the IPC message, but it is very intricate to create and initialize a connection through render RCE. Therefore, we leaked a PP instance ID and used the PPP sunk structure to send the IPC call using the existing connection. The structure of PPP sunk is shown in finger. There are global variables in render process holding the address of the functions. We can specify a connection to send the IPC message by passing in a PPP instance ID to these functions. And the PPP instance ID is stored in a global map. We also can leak its value. Taken together, we could flexibly call the legacy IPC for subsequent exploit. And about the bug, there is a very common pattern in Chrome Sandbox vulnerabilities. A member variable keeps a row pointer or a smart pointer, and the row pointer is not cleaned up after the smart pointer is destroyed. The row pointer becomes a downlink pointer, and the vulnerability will be triggered when the pointer gets access. The root cause of this bug is similar, but kind of different. The victim pointer leading to user free in this bug is wrapped as a weak pointer. Let's first take a look at the passing path of this pointer. The target smart pointer stores in map resources, and its row pointer could be taken out, wrapped as a weak pointer, and stored in a member variable or paper file reference host class. Another class, paper file IO host, can overturn this weak pointer and keep it in a member variable named file system host. After checking the cross-reference of the map resources, we found that the key of the map could be passed in from the run side. Therefore, if we pass in a duplicate PP resources, the previously stored target smart pointer will be destroyed. However, its row pointer, which is wrapped as a weak pointer, is still stored in file system host. The use.free will be triggered when it gets used. But the type of file system host is weak pointer, which means the row pointer will be checked whether it is valid before use. However, due to the compiler's optimization of undefined behavior mentioned before, the check did not take effect. And about the exploit. After tracing the cross-reference of file system host, we found that the function create file system operation is the final virtual call which we want to use. We at first want to spray blob to replace the freed object with a buffer containing completely controlled bytes, but due to the virtual table call is more in depth, we now need to construct the structure to meet the constraints on this path and hijack the control flow. On Windows, if a library is loaded in multiple processes, it will be at the same base address. So the library loaded in the render process will be loaded at a known address in the browser process. Therefore, we not only need to leak the hyperaddress to achieve our exploit. At the beginning, we try to use shared buffers as mark-rand. He used the shared buffers between the render and the browser process to do hyperstringing to predict the hyperaddress. but it needs to spread around 4 TB or copies of the page. And after he proposed this exploit, the Chrome team has set the limit on how shared memory can be mapped in one process to 32 GB. So maybe we need another way. So we found a call path that will send the contents of a 4-byte member variable or file system host to the render. And we found a class SSL error handler which has the same size as file system host and has a have address at the offset we can send. We finally destroyed the resource host by using rest condition after meeting the constraints and before sending the reply, and replace the free space with SSL error handler. So we send the 4 bytes or hyper address to the render process and change the code by render RCE to receive them in the render side. At this point, we have leaked the higher 4 bytes of the hyperaddress. So we can predict the hyperaddress by spraying around 8 GB data through the way macrand used. It's little than 32 GB. And we then reuse the use.free to do the virtual code to pivot the stack to the spraying data and finally achieve arbitrary code execution through IOP. Okay, that's all about the exploration to escape the Chrome Sandbox in TNF Cup 2020. Now let's watch a simple demo video. Okay, that's all. And about the conclusion. In this presentation, we first briefly introduced the background of Chrome multiprocess architecture and its interprocess communication system. We described the significance of variant analyze and how it works with CodeQL. After that, we review some classical bugs and introduce how to generate more abstract and complex vulnerability patterns and locating potential bugs quickly. Also, when analyzing the vulnerability pattern mutation, we introduce 3 patterns from the shallow to the deeper about random host, return, and wake pointer optimization. At last, we take a bug that we use to escape the Chrome Sandbox in TNF Cup 2020 as an example to introduce how we do the exploit. Okay, that's all. Thank you all for listening. And is there any question?